Hello everyone. Before we start this PCB design series, it's important to know why do we need PCB design. Maybe you have an idea that you want to implement. Let's say you want to build an IoT watch that can turn on or off your room's lights. Or maybe you want to build a tiny drone. Or maybe you want to make your own electronic business card. PCB design makes it possible to convert your ideas into actual tools. You can create your own custom tools and solutions instead of waiting for someone to invent them. Most importantly, if you are a student entrepreneur, PCB design gives you the ability to convert your prototype into a product. In this workshop series, apart from building a strong foundation in PCB design, you will learn to think. You will learn to think logically as someone who builds systems that can work reliably. This problem-solving mindset and logical thinking goes well with any career. Whether you end up launching your own startup, joining an R&D team, or making your own prototype, or maybe just a cool guy who can make ideas into actual hardware. So, with that being said, let's start our PCB design journey. Throughout this series, we'll use an open source software called KiCad to design our PCBs. You can get it by just typing KiCad on Google, go to their website and click on download. So based on your operating system, you can download for Windows, Mac or Linux. So currently I'm using a Windows version. So I'll just click on any Asia server. Then you can just save the setup. Once your download is complete, you can double click on the setup file and just follow these default instructions. Click on yes, click on next and install on whichever directory you would like. So I'm not going ahead with install because I have already installed it. Now once you have successfully installed the software and open it for the first time, you will see a similar window. Don't worry, we'll go to each one of these options as we progress on with our series. But for now, we'll just create a new project. Okay, and the first project that we're going to work with is a motor driver. Okay, so let's just name it motor driver and click on save. Now your new project is created. You can see two files are being created. One is PCB and one is schematic. So schematic is the logical or the circuit diagram and PCB is the physical layout of this circuit. So we'll go step by step. So let's just go to schematic. You can also click here. Once you click on schematic, you'll see this window. So here is where we'll design our first circuit. At first, this window seemed a bit overwhelming with all these options, but don't worry, as we progress in this course, you'll be comfortable with all of them. Now, the very first thing that you can do is go to File and go to Page Settings. Here, you can include the basic details of your project. So, for example, the issue date. So, if you click here, it will just grab today's date and put it there. Revision, this is the first one, so 1.0. Title, so this is an L298 motor driver. Okay, and hit on OK. So as you can see, we have our title displayed here. Now before proceeding with the actual schematic diagram, let's just first see what we're actually trying to build. This is an L298 motor driver and this is the first project that we'll build together. If you haven't seen this motor driver before, it is a simple circuit that is used to control two DC motors. You'll see a variety of components here. For example, these capacitors, these pin headers, these connectors, some diodes, resistors, and one LED. The main part or the main IC that is being used here is this L298 IC. This IC has the following pin diagram, where each pin has its own specific purpose. Okay, so first VSS, it is used to power the internal logic of the circuit. VS, it is used to power the motors. Enable A and enable B, it is used to control the speed of the motors. Send A and send B, it is used to sense the current. Input 1, input 2, input 3 and input 4. These are the 4 pins that controls the direction of the two motors. Out 1, out 2, out 3 and out 4. This is where you will actually connect your motors. This L298 IC works on the fundamental concept of an H-bridge. Here is a simplified version of how it works. So let's say switch 1 and switch 4 is closed. Then current will flow in this direction. So let's say the motor will move in clockwise direction. Now let's say switch 3 and switch 2 is closed. Then current will flow in this direction. So as you can see, the current direction has reversed. So the motor will move in this direction. So this is a very simplified example on how H-bridge works. Now let's say we want to use this L298 to make our own circuit, but we don't know what voltage does it operate in or what voltage should I supply. This is where the components datasheet comes into the picture. Now, what is a datasheet? Well, a datasheet is an official technical guide on how to use it, how to not use it. It will contain information regarding the max voltage you can use, the max current it can output, and all the other technical information. So, how will you get the datasheet? You can just simply type L298 and datasheet. So this is a data sheet given by STM Microelectronics. We just click on it, and here we have all the information we need to build our circuit. When we scroll down to its electrical characteristics, we can see that Vs, which is the supply voltage, pin number 4, can have a max voltage of 42 volts. And VSS, which is the logic supply voltage, it needs 5 volts. The difference between VSS and VS here is Vs, which is the supply voltage, it will be used directly to power the motors, while VSS, which is 5 volts, it will be used to power the internal circuitry of the L298 IC. So now that we know from the datasheet that what voltage we need to supply, let's just go to our schematic editor, add the L298 IC and give it some power. To add any component in the schematic editor, you can either go to the right side and click place symbols, or alternately you can just press the A key in your keyboard. So it will take some time, I think around 45 seconds to load all the footprints. Don't worry, we'll also learn about footprints as we progress with this course. But for now, let's just not complicate things and wait for it to load. So once it's finished loading, you'll see this kind of a window. Now you can simply type the name of the IC that you want to add and click OK to place it. For example, I'll just type L298 and see, we have got this in the item driver motor L298 and if we click OK, we can see this component is being placed into the schematic editor. Now we can click anywhere to place it. So we have successfully placed it. Now we see the pins that we need to power, VS and VSS. Now typically you will have a 12 volt battery or a 9 volt battery. Now the problem is, although in VS you can supply up to 46 volts, but the internal logic requires 5 volts. So how are we going to convert 12 volts or 9 volts to 5 volts? Well, we'll use another component called a voltage regulator. Okay, so we'll place another component, we'll press the A key, we'll type 7805. Don't worry if you're not familiar with the terminology. IC 7805 is just an voltage regulator. What it does, it takes up to 35 volts and converts it into 5 volts. Now, how it does that is another story. Maybe we'll cover it in some Q&A sessions, but let's not complicate things and just place our voltage regulator. So here we have our voltage regulator with three pins in, out and ground. So we'll just place it. Now this is where the importance of datasheet came into play. See, if we go into the datasheet which I have already downloaded for 7805, you'll see some interesting things. If you scroll down to layout example, you'll see that two capacitors are being used with these voltage regulators, and we'll cover it in more depth in the next session. So for now, just understand that this C1 capacitor at the input side, it helps the regulator to handle sudden load changes in the power supply, and the capacitor C2 in the output helps in keeping the steady voltage of 5 volts. So let's just go back to our schematic editor and add the two capacitors. So we press A to bring the list of components, then we press C for a capacitor. Now you will see two different kinds of capacitors here. One is this polarized and one is this unpolarized capacitor. We'll go in depth into capacitance in the next session, but for now, just know that if we are using some polarized capacitor, then the polarity of the voltage will matter. And if you are using an unpolarized capacitor, the polarity, it doesn't matter. So we'll use a polarized capacitor and place it near N. Now, after we have placed the first capacitor, we don't need to go again, press A key and select it again. We can just hover our mouse over this capacitor, then press Ctrl D to duplicate it and place another near the outside pin. Also, if you hover your mouse over a component and press M in the keyboard, then you can move it around. So let's just place it here and this capacitor here. Now how do we connect this? Well, there are two options. The first is you can see a tiny circle here. As I point my cursor to the circle, I see a crosshair appearing. So if I just click, it will draw a wire. So now this output is connected to this polarized capacitor. Similarly, if I press W on the keyboard, then also it will draw wire, and you can press escape to go back to the selector. Now to add value to capacitors or resistors, you can just double click it and click here on value and put any value that you want. So we'll use a 220 microfarad capacitor, and here also the same. This small u means microfarad. Click on OK. So now we have two 220 microfarad capacitors. Now, as you recall from the datasheet, we need to supply 5 volt to this VSS pin. And where we are getting these 5 volts from? We are getting it from the output pin of this L7805. So we'll just draw a wire from this output pin to the VSS pin of L29N. So now we have successfully supplied 5 volts to this IC. Now you may notice that we haven't added any batteries or any connectors as of yet. This is where generic connectors comes into play. So generic connectors are just some pins or some sockets that the PCB uses to connect to external power supply or external pins. So since we're providing some external power, so we'll be using some generic pins to supply the power. If we go back to this diagram, you'll see these pins. So these are all pins or connectors that are being used to connect to some external circuitry. So these two on the side, these are marked as out 1 and out 2. These are used to connect to the motors directly. These three that you can see here are used to power up this L298N. And these pins that you can see here, these are used to control the direction and the speed of the motors. So let's just place some connector pins in our schematic diagram so that we can connect it to some external circuits for power and inputs. So back in the schematic editor, we'll just press A to add new symbols and type connectors. So you'll see under item, you'll see a different lot of connectors. For power supply, we need 3 pin connectors. So let's just place them somewhere here. And we have two motors. So we need this 1:2 pins. So let's just place them here and duplicate it for the second motor. And we need 1, 2, 3, 4, that is iron 1, iron 2, iron 3 and iron 4 for the inputs. So let's just grab 1:4 pin and let's just place it somewhere here. Okay, so now these pins that you see here will be used to supply the power. Now I'll put some text to visually help us understand which pin is supplying power. So you can go to the right side menu and click on draw text. So let's just say 12 volts. Press OK. I'll press it somewhere here. Then I'll press another text. Make it ground. Click OK. Press it somewhere here. And I'll click another text. This is 5 volts. Note that this text is only for our visual reference. It has no electrical purpose. Now we're going to connect 12 volts to the input of this voltage regulator, and for placing ground you can go to the right side and place power symbols. Click on it, type G and D, you'll have your ground symbol and you can add your grounds. So let's add some grounds. I'll press Ctrl D to duplicate it. Press another ground here. Ctrl D to duplicate it. Press another ground here. Press Escape and connect these three grounds. And I think we need another ground here. I'll click on it. Press Ctrl D to duplicate it. You can also press R to rotate it. So if I click R, it gets rotated. So I'll just place my ground somewhere here and connect it. Now note one thing, that these two wires may seem crossing each other, but they are not electrically connected. The wires will be only connected if there is a small circle appears. This means these two wires are electrically connected, but these two wires are not electrically connected, although it may seem visually that they are overlapping each other. Now we're going to connect this Vs to this 12 volt. Since we can supply up to 46 volts, so we're just using 12 volts for now, because most commonly we'll be using 12 volts or a 9 volt battery. Now let's just try connecting our input pins. So I'll just begin the wiring from iron 1 to here, iron 2 to here, iron 3 to here, and iron 4 to here. Now notice one thing, as the complexity of the circuit increases, this wiring, it might get messy and even we might do some mistakes. So there's a neat way of doing it. So I'll just delete these wires, press on the delete key, click on the wire, press on the delete key to delete the wires, delete these bottom wires also. The cleaner way of connecting two nodes when the circuit is relatively complex is by using something called as net labels. So on this right side, you'll see something called as place net labels. Okay, if I press here and give it a name, let's say input 1, click on OK, you'll see we have a label for input 1. Similarly, we'll use duplicate for input 2 and duplicate R to rotate for input 3, duplicate R to rotate for input 4. And now we'll just copy these four labels and connect it here. Now, how do you copy multiple labels? You click on one label, hold the shift key, click on another label, click on another label, and press Ctrl D to duplicate them and place it here. Input 1, input 2, input 3, input 4. I'll just bring it up slightly. Now, just connect them. Now, although it seems that these pins are not connected visually, but electrically they are connected. So, this pin 1 is actually connected to this iron 1. This pin 2, this pin 2 is actually connected to iron 2. And what we have used is net labels. So, let's just put similar labels for ENA and ENB. For that, we need to add two more connector pins. So connect a pin. That's okay. Let's just place it here and duplicate it. It's another one. Now, now just place some labels. Let's say ENA. Place it here. Another one. Place it here. Name it ENB. Copy them. Duplicate them and connect them here. Now this pin 1 is actually connected to ENB, and here this 1 is connected to ENA. Now you might wonder that why have you used two such pins, right? We could have used a single pin. There is a reason for that. So if we see our circuit diagram, you will see, let me rub this real quick, delete this. You will see that this is a jumper. Similarly, this is also a jumper. So, by default, these pins are actually connected to 5 volts. Okay, this by default it is connected to 5 volts. So, when the jumper is placed there, these pins are connected to 5 volts. That means when you will control the motor, when the jumpers are in, it will go on full speed. But if you want to control the speed of the motors, then you first need to remove this jumper. You need to remove the jumper and put some PWM signals in it. If you want to control the speed, you need to remove the jumper and put some PWM signals in it. Now that is a very different topic since we're currently focusing on PCB design. So let's just get back to our circuit. Now, similar to these net labels that have some specific names that we can give, KiCad also has some power symbols that we can use. For example, we can see that this wire that 12 volt is connected to Vs, but we can just use a power label to electrically connect them. So let's just go to this power labels. Just go to power label, type in 12. You'll see plus 12 volt. Click on OK, and let's just connect it here. Now this wire is irrelevant, so let's just delete this wire and copy the symbol to this 12 volt. Now this looks way more clean after deleting this wire. Now similarly, we'll place a 5 volt power label. So we'll click on power labels, type 5V plus 5V, press the R key and place it here. Now you can see the text is being slightly irrelevant here, so I can just delete this text by clicking on it and press on delete. I can delete this text also. So this 3 pin is now connected to 5 volts. Similarly, we can just delete this wire, delete this whole wire, and copy this symbol, duplicate it, click on R, and place it here. Now these 2 pins are actually electrically connected. We'll also need 5 volts here because we're getting the 5 volts from this voltage regulator. So I'll briefly summarize what is happening here. These are the external pins that you see here. These 3 pins is exactly these 3 pins. So in one of them we'll supply our battery and one of them will connect to ground. And this 5 volts, it will be actually supplied by this voltage regulator, and this 5 volt will also go to our IC, to our L298 internal logic circuitry. I hope this power management is clear. Now, before we move on to these output signals and the sense A and sense B signal, there is one more little tricky thing that we need to consider. See, in this L298 circuit, there is another small jumper here, this tricky one, this one. And what it actually does is it's connect the voltage regulator to the input. If these jumpers are connected, by default, this jumper is already placed. So it means these 2 pins are connected. That means we are giving power to this voltage regulator. This is the voltage regulator. But if we remove this jumper, then the power won't ever go to this voltage regulator. We won't be using it. Okay, so if we remove the jumper, then we actually need to supply our IC. This is the IC, some 5 volts. Okay, so 5 volts. If we remove this jumper, then our IC needs to be supplied 5 volts, because if we remove this jumper, this voltage regulator gets disconnected. But when this jumper is connected, then this pin is actually giving out 5 volts to the IC. So to sum it up, if you are placing the jumper, then the voltage regulator is connected and we don't need to give 5 volts to the IC. But if you remove the jumper, then we need to give 5 volts to the IC. Okay, so we need to add this jumper to our circuit. So let's just do that. So I'll just copy this connector, Control D, I'll place it here, and now I'll delete this wire and redraw it like this. Now if we put the jumper in the voltage regulator, it will get the input power. But if we are not uh, putting the jumper, then we need to actually provide 5 volts to this VSS pin. Okay, so I think almost all the power pins are covered. We have successfully powered on our little motor driver here. Oh, I just forgot to put one ground. Let's just quickly put that here. Now the remaining pins that we need to connect are these motor pins and these 2 sense A and sense B pins. Typically, in almost all the circuits that you will see, the sense A and sense B will be grounded. But actually, they are used to measure the motor current. So, we'll actually try to implement that. The commercially commonly available alternating motor driver, in that board also the sense A and sense B is grounded, because for common hobbyists we don't need to measure the current, but just for learning purpose we are going to actually make a tiny improvement in the circuit by actually measuring the current. Okay, So in this circuit, you can see this motor driver, these two sense A and sense B pins, they are typically grounded because we don't actually use them very often. But for learning purpose, we're going to use some small circuit to detect the amount of current. And this out 1 and out 2 will also be connected to the motor pins. Okay, so let's just first connect the motors. I'll rotate it. I'll rotate this one too. Move it a bit further. Move this one a bit further too. Okay, so let's just connect these wires quickly. Okay, we need to adjust a bit. It's fine. Now you can actually press the G key to move your components without breaking the wires. Right? You can see that if I move it around, the wires are still intact. But if you press the M key, it might move your connection. See, might move your connection. So we can use the G key to make some minor adjustments. Now here comes the tricky part. Actually, we cannot just connect these output pins to the motors directly because there is a fundamental reason behind it. So let's just find out why we cannot directly connect it. So this is an internal structure of the motors. Okay, inside a DC motor, there is a coil of wires. Now, when you suddenly stop the motor driver, the motor actually acts as an inductor. So, as a property of inductor, it resists the sudden change of current. So, let's just see what happens when you suddenly stop your motor driver and why we need some diodes in our circuit. See, when the motor driver is on, the current will flow through the motor. Okay, if you suddenly stop the motor driver, the inductance in the coil of the motor will resist this change in current. So when the motor driver is on, the current will flow through the motor. And when the motor driver stops suddenly, the inductance in the motor, it will resist this current change. What the motor wants, it wants the current to keep flowing in the same direction. But we have stopped our supply, we have stopped the motor driver. So to resist this change of current, what the inductor does or what the motor does, it increases the voltage. It increases the voltage so that current keeps flowing. Now let's just say these are the output pins through which the motors are connected. So this is our motor, right? And this is our IC, right? This is an IC. There's a lot of other pins, and there are some transistors here. Okay, so there are some transistors. I'm simplifying the diagram to help you understand. See, the current is flowing, right? The current was initially flowing. The current was flowing something like this. Okay, but now you have suddenly stopped the motors. So inside these motors there are coils, right? So they act as inductors, and you know it's a property of inductors to resist the sudden change of current. Okay, so to make the current flow continuously in this direction, it will induce a voltage. Okay, it will create a voltage. And how will it create a voltage? It will collapse its magnetic field. So whenever current flows through inductor, it generates a magnetic field, and now the current stops flowing, but the inductor wants the current to flow, so it collapses its magnetic field and induces a voltage here. So this voltage will help the current to flow in the same direction. But if we don't have a safe path for this current, then our transistors might get damaged, because currently when we have stopped the motors, then this is in reverse bias. These transistors are in reverse bias. And If the current continues to go through them, then it might damage the transistors. So we need another safe path for this current to flow. That's where the diodes come into the picture. So what these diodes will do, they will give a safe path for this current to dissipate. Okay, so let's just say this is the output from the IC output for the motors, right? So we have the motors here, we have the motor one here. Sorry, there is only single motor for two outputs, right? Then we'll introduce some diodes here. Okay, introduce some diodes here. So, what these diodes will do, they will give a circular path for this extra current to dissipate. Okay, depending on some cases like braking or reversing, there will be a loop formed by these diodes. There will be loop of current formed by this part of diodes that will help the current to dissipate. Okay, so this is a very small flow diagram. So motor driver turns on, then current flows through the motor, then motor driver suddenly stops. This due to the inductance property because there is a coil inside the motor, this which will resist the current change, and thus it will increase the voltage. Why it will increase the voltage? Because it wants that current to flow in the same direction even after the motor driver has stopped. Now, if there is no safe path, then it can actually damage the transistors inside the IC. Okay, and transistor junction breakdown can happen. But if you have a path using some diodes, then current will circulate through that diode loop and energy will dissipate gradually. Okay, the energy, it will be used up as heat in the motor coil itself, and there will also some minor voltage drop across the diodes, and it can also return through the capacitor to the power supply rail. Okay, so that is why we need some diodes to give this current a safe circular path to dissipate its energy. Okay, so let's just put in our diodes in the KiCad schematic. Before adding the diodes, let's just delete these wires quickly. Then we press A to add a new component. We type 1N4007 is the name of the diode. It's a very common diode. So we press R to rotate it. We need 4 of them at the top. 2, 3 and 4, and we'll duplicate it. 4 of them at the bottom. We'll just move it aside. Then we're going to connect these diodes quickly. Give it a turbo supply. Place the ground, and now we need to connect these output pins to these motors. So let's just do that. Output 1, output 2, output 3, output 4, and we also need to connect these to the motors. So bring them a little forward. I think that's fine. Connect it here, this one here, this one here, and here. So I think almost all of the circuit is done except for this sense A and sense B. Now you might get a little confused on what is the return path of this current, right? What is the circular path? So please remember one thing, that all these grounds Okay, all these grounds, they are connected. Okay, this capacitor is connected to this ground, right? And there is a 12 volt supply here. So this capacitor is also connected at this point. Okay, it might seem a little hard to visualize, but you see there's 12 volt supply, there's 12 volt supply coming in to capacitor and ground. So 12 volt supply coming in, then there will be a capacitor and ground which is also connected here. So to form like a loop, to form like a loop for that excess current, and it will eventually dissipate into heat. Okay, now the only thing that is left is sense A and sense B. So these are the two pins which are used to measure the amount of current. So let's just quickly deal with those two also. I'll move this a bit on the side to make space. Okay, I think this is fine. Now to measure these two currents, we need a very small amount of resistance. Okay, so I'll just bring one resistor R and place it around here. It's fine. I'll move this text over here. This would be a value of 0.1 watt because we are trying to measure the current. Place it here. Okay, duplicate it. Place it here. Move this R to the side. I think that is fine. Now just connect it. Now to sense the current, we're going to put something called as a test point. So a test point is just something where you can put your oscilloscope to measure that signal. Okay, this is very simple. So this is test point. Place it somewhere here. Then connect it here. Similarly, I'll just duplicate it. Control D, press R, place it here. Draw the wire. Okay. Now, uh, now, what this will do is, if you put your oscilloscope probe into it, it will give you the signal current or signal voltage that you want to measure. Ideally, what you want to do is actually use a low pass filter, a simple low pass filter using a resistor or a resistor and a capacitor to filter out this signal. But I think I have overcomplicated this project enough, so we'll skip that for now. But just know that the sense A and sense B is used to measure the current. Okay, current in the motor. So I think with this our schematic diagram is complete. Don't worry, at first it might look very dangerous or very tough, but once you get the hang of it by doing it yourself, it will find it's a very easy circuit. Okay, I'll just summarize what we did today. First, we gave power supply to Vs. Okay, we gave power supply to Vs, that is 12 volts, because we'll typically use some 12 volt battery. And where this 12 volt is coming from? It is coming from these connector pins that you can also see here in our diagram, these three pins. So this is where we'll supply the power. So these pins are just external connections. Okay, whenever you see these pins, like here and here, these are just external connections. Okay, so our 12 volt is coming from here. Then we are also giving this 12 volt to this voltage regulator, who is giving us 5 volts output, and we're connecting that 5 volts output to supply the internal logic of this L298 driver circuitry. Then there are input 1, input 2 for motor 1, input 3, input 4 for motor 2 to control its direction, enable 1 and enable 2 to control the speed. So these are the input pins. Again, if you see connector pins, you will know that these are some external connections. For example, this here, these are the input pins. So this is, I think, ion 1, ion 2, ion 3 and ion 4. Okay, this is E and A, E and A, and this is E and B. So these are the connections. Next, what we connected was these diodes. I think I have over explained why we need to use diodes, because the motor, they might behave as inductors and which can destroy our transistors. So we gave them a safe path to circulate through their coil and dissipate their energy. Okay. So this is all for this schematic. So we introduced some very basic concepts. Next, what we're going to do, we're going to actually make the physical layout of the circuit. This is just the electrical and the logical circuit. But when we want to fabricate it, when we want to manufacture it, we'll have to actually draw the physical diagram. So from the next session, we'll dive deep into that. We'll also cover why we're using some capacitors, what's polar, what's non-polar, how do we use it. We've also briefly touched on datasheet. So I hope this session will help you at least start your own project. And from the next session onwards, we'll continue our journey with this PCB design series. Thank you.